Section 9, Part 2. You're looking at the bottom of page 24 of well, it's the first page of the third note packet. And we're down here to where it doesn't say much of anything at all. It's just a little outline of what I'm going to go over on the blackboard here. The definition for angular momentum and the angular momentum of a rigid body. And the story goes like this. Slightly higher. That's probably good. So let's start out with the angular momentum of a small particle and then generalize from there. Definition of the angular momentum of some point-like particle. I mean, the best example would be an electron shooting along through empty space. As near as anybody's ever been able to measure, electrons really are point-like. Whatever the radius of one is, it's smaller than we can see with current technology. So here's a picture. There's the particle. Its momentum, its linear momentum, from a few weeks ago, is its mass times its velocity vector. So maybe it's heading in that direction. Relative to this origin here, it's located at the tip of this radius vector, r. Just as the rotational effect of a force depends on how much leverage it gets, that was the idea of torque, okay? In a very analogous way, the rotational effect of a body's momentum also depends on how much leverage it gets. Don't ask me why they use the letter L for angular momentum. I guess the answer is why not? But whatever symbol you want to use for it, and some textbooks do use other symbols, but when you form a cross product with a radius vector, that is called a moment. Torque is the moment of the force, R cross F. Angular momentum is the moment of the momentum, R cross P, okay? Now, what if instead of some small point like, well, it doesn't have to be small, this could be the Earth orbiting the sun, but whatever object it is, it's small compared to the length of this radius vector, small enough to say all the mass is located at a single point. Well, what if that's not even approximately true? What if you have some rigid body, like a door rotating around its hinges, or a lawnmower blade spinning around its center, or, you know, this is like the 10,000th time I've said that. So, a rigid body instead of a single point-like particle. And this is not the first time I've gone through this type of thinking with you either. Here we have some generic rotating object, which is, you know, this is the axis of rotation right here. It passes through the page at that point. And think of it as a whole bunch of little pieces stuck together. This one has a mass M1 and a radius, it's going around in a circle of radius R1. And this one next to it has a mass M2 and it's at a distance R2 from the pivot point. And if I keep labeling things like that, I'm pretty quickly going to run out of places to write. But the idea is you just keep going like that, dividing the whole body. I'm gonna stop drawing because I don't feel like doing this all afternoon. But you divide the whole body into lots of little pieces. The angular, well, each one of those little pieces is the thing I was just talking about back here. The angular momentum of each little piece is R cross P. So the total angular momentum of the entire body is R1 cross R1 cross P1, where P is equal to mv. That's the angular momentum of that little piece. That is the angular momentum of the next little piece. And there's a lot of other terms that I don't feel like writing down. Be expressed a little more compactly by writing it as a summation. The lowercase I is the index of the summation. I equals 1 in the first term, I equals 2 in the second term, and so on. Okay, that's all that is. For the rest of this, I have used the definition of the cross product. The cross product of two vectors is the magnitude of the first vector, so the magnitude of R, times the magnitude of the other vector, which would be, I suppose I probably should have had some subscripts on the M's also, because there's no guarantee that all of my pieces are the same mass. So magnitude of the first vector, magnitude of the other vector, which is the momentum, sine of the angle in between. Well, if these particles are part of a rigid body, they have no choice but to go around in perfect circles, okay? When you've got just an individual particle, like a comet orbiting in our solar system, then that could be moving in any direction, and theta could be, in principle, any angle. But if it's embedded in a rotating object, there's only one, it can't move farther or closer to the center without breaking up the object. So it's got to go around in perfect circles, and the direction of motion is always going to be perpendicular to the radius. And so that's 90 degrees, and the sine is just equal to 1. So cross product, magnitude of the one vector, magnitude of the other vector, sine of the angle in between, and a unit vector normal to the two vectors being multiplied. Should all sound kind of familiar from a few weeks ago. Well, actually, probably about 1 week ago, the unit on torque. Time for a substitution. Recopy the R. That's just a 1, so that's gone. Recopy the M. As for the V, V is equal to times omega. This is one of those relationships where you have to use radians. V equals R times omega. So the end result of this is going to be another equation where radians are required. Omega does not need a subscript. Every particle has the same angular velocity because it's a rigid body. There is no way that a piece out here could take 3 seconds to go around, but a piece closer to the center take 2 seconds to go around once. The only way that could happen would be if you break it. If it's a solid object, every piece of it has to take the same amount of time to go around once. And so you've got the same angular velocity. There isn't any omega 1, omega 2, it's just omega. Let's rearrange a few things. Combine the two r's into an r squared. And then this is the distributive property. Omega is the same on every term in this summation. Likewise, the unit vector is the same on every term in the summation. So they can be factored out, leaving you with the summation of the mr squareds, or summed over all the particles that you divide the thing into. This is the definition of the body's moment of inertia. And of course, to get an exact calculation of the moment of inertia, you have to take, I explained all this in the past, but just to repeat myself, you have to take the limit of infinitely many, infinitely small particles. This summation becomes an integral in the limit. So that's the moment of inertia. Over here in the other set of parentheses, you have the magnitude times the direction of the angular velocity vector. So the moral of the story is the angular momentum of a rigid body can be found multiplying its angular velocity times its moment of inertia . Don't forget to use radians. I've lost my place. Hold on a second. Okay, I confused myself for a moment, but I'm all better now. We are here. Example number 4, section 9, example 4, which just simply says to find the angular momentum due to the Earth spinning on its axis. So I'll point you over here, and I will do that. The Earth is more or less a rigid body. Parts of the interior are liquid, but that's not going to concern us too much. So I times omega, which you can't see me pointing at because it's off the edge of the screen now, but hopefully you remember from a minute ago. So I need the Earth's moment of inertia, and I need its angular velocity, and I multiply them together, and that's the answer. Earth is a solid sphere. You look at your formula sheet and it says a solid sphere is 2/5 mr squared. Elsewhere on your reference handout, you can look up the mass and the radius of the Earth. Sometimes call it the reference sheet, but it's actually 4 or 5 sheets stapled together. Whatever the right name for the thing is, there's a place in there where you can look those numbers up. And now, as is often the case in an introductory course like this one, there are some simplifying assumptions that have been made here that mean that this is not exactly the correct, I mean, it's a decent estimate, but this is not exactly the correct figure for the Earth's moment of inertia. And at this point, I usually look out over the class and say, anybody got an idea why? And I'm standing here in an empty room. So of course, nobody says anything back to me. So I'll have to now say, well, actually, some answers I've gotten in the past, people say things about, well, you know, the Earth is not perfectly spherical. Yeah, that would have a very small effect on this, but there's something that's more significant. And that is the fact that the Earth does not have a uniform density, okay? This formula is derived assuming a sphere that's homogeneous. You've got a uniform density throughout the whole thing. The Earth is in fact denser in the middle. When the Earth was very young, it was all melted, and denser things sank into the center, and lighter things like rocks floated on top. And then a few 100 million years, and the Earth solidified and became a solid object, but by then it had differentiated. So the Earth's core is denser stuff like iron. And so what do you think? Is this a little too high or a little too low? And I'll give you a couple of seconds to form an opinion. The true moment of inertia would be a little bit less than this, because being denser in the middle means that a little more of the mass is a little closer to the center than we assumed when, or well, we didn't go over how this is derived, but the assumptions built into this, it's moment of inertia is more when mass is farther out. Moment of inertia is less when the mass is closer in to the axis of rotation. So if the Earth is denser in the middle, then some of the mass is a little closer in than was assumed in deriving this. So this number would be a little on the high side. Anyhow, the Earth's angular velocity. And I always turn around and say to the class, everybody in this room knows the Earth's angular velocity as it spins. Maybe you haven't quite connected with the fact that that's what you should call it, but I'll give you a moment to think about it. The Earth's angular velocity is 1 revolution per day. What is a day in the first place? after all. But there's that whole pesky thing about how it's got to be in radians per second, revolutions per day. Oh, that would just be too convenient, I guess. So the usual unit conversions that you've seen before, 2 pi radians equals 1 revolution. So revolutions over revolutions cancels like that. 1 day equals 86,400 seconds. Actually, I think there was an example a month or so ago where I mentioned how I should really be using a sidereal day, not a solar day, and there's a difference of about 4 minutes, but, well, not getting distracted by that. Our surviving units here are going to be radians per second, which is what we need. So 2 pi divided by 86,400, which is 24 times 60 times 60. That comes out 7.27, 10 to the negative fifth. Radians per second. And to get the Earth's, now this would be its spin angular momentum, which is actually significantly smaller than its orbital angular momentum from going around the sun. But the spin is what the question asked for. So this I times that omega, I'm not going to bother writing them down again, but you put them together in your calculator and it comes out 7.07 times 10 to the 33rd power. Kind of an ugly bunch of units on there. That has no name of its own. They haven't named that after anybody, but for something a little more compact, sometimes you see it written joules times seconds, which I don't know if it's exactly appropriate to use a joule in that way, but sometimes you see it done. So that is the answer to number 4. And then we get to, maybe I don't need to point it at this, just to have you look at 5 words. What it says on the sheet next is conservation of angular momentum. If there are no external torques, you know, somebody might be taking notes from what's on the screen. I should probably, not taking notes, probably should be. But you might not be bothering to write this part down if you printed off a copy of it. Focus. Come on. Okay, there we go. If there are no external torques, it kind of mirrors the language for conservation of linear momentum. What I said a few weeks ago was that in the absence of any external forces, momentum is constant, both in magnitude and in direction. So you just replace the word force with the word torque and so on. In the absence of any external torques, a system's angular momentum is constant. As an example, I've once again dug out our old friend here, the cork on the, you know, it goes through the pen barrel. Spun that around for that lab a little while ago. And do this here, just a second. If I do it there, I'm going to hit the wall. Just to kind of demonstrate what's going on in the next example. Okay, so I've got that going around like that, and I'm going to pull the string and make it get shorter, and you're supposed to notice that it makes the thing go around faster. Right now, it's probably less than 1 revolution per second, but if I do this, the shorter it got, the quicker it was going around. It's not a perfect system. There's some losses to friction and so on, but that gives you the general idea. So aiming you back at the question, it just puts some specific numbers on the situation you were just seeing. And given the initial speed and how much the length of the string changed when I pulled it, you're supposed to calculate, well, actually, I'm supposed to calculate the final speed. First of all, good to ask yourself if this is a situation where cords are getting all tangled up, so I can't move anything without. Okay. Okay, that's a little better. Is this a situation where angular momentum should be conserved? Yes, because as that cork goes around, well, in a horizontal plane, I mean, there's gravity pulling down and there's a Y component from the string pulling up. But as far as any forces in a more or less in a horizontal plane, there's just the tension in the string. The tension in the string points right straight toward the center, and central forces produce no torque, okay? You've got a radius vector that points from the center out to the cork, and you've got a force vector that points right straight back toward the center again. And those two vectors, when you put them together, make a 180-degree angle. Sine of, r sine theta f, sine of 180 is 0. A force that passes through the axis of rotation produces no torque. I can't open the door by shoving on the hinges, no matter how hard I push. Forces that pass through the axis of rotation produce no torque. And therefore, since there is no torque, angular momentum should be conserved. So, having established that, L final equals L initial. Well, we've got basically two equations floating around here. There was the one I started with for a point-like particle, which to a decent approximation, this thing is. Size of the cork is fairly small compared to the length of the string. It was R times mv for a point-like particle. And then there was the other one that's what you really want when it's an extended object, I times omega. Well, in this particular case, since it doesn't say find the angular speed, it gives you meters per second initially and says find speed, not angular speed for what you're looking for. So probably we want to go for the one that's got a V in it, since it's V we're looking for. So angular momentum is R times mv. The final value of that is equal to the initial value of that, the moment of the momentum, R times mv. Very analogous to R times F for torque. There's a factor of the sine theta also, but that's equal to 1, assuming something is following more or less a circular path. The mass of the cork does not change. If it's 30 grams here, it's still 30 grams over there. So you divide through by m and it's gone. I divided both sides by R final to solve it for V final. So it turns out we have just a simple inverse proportion here. There's a trade-off between the radius and the speed. Everything's to the first power, and when the radius is big, the speed is small. When the radius is small, the speed is big. Filling in the numbers. 75 centimeters to begin with. The radius shortens down to 25 in the end. No need to convert the centimeters into meters to match this because they cancel each other. It's a 3-to-1 ratio is all that matters. Although if you want to change them into meters, when in doubt, convert to standard units. Not always necessary, but never wrong. So 1/3 the radius, 3 times the speed. One example that people like to give of this sort of thing is when you see figure skaters spinning around. They get themselves going and then they pull their arms in, and that makes them spin even faster. They're changing their moment of inertia, bringing the mass of their arms in closer to their body. And as well, that would, rather than, it's the same general idea, but you probably want to think of it this way. If you make the moment of inertia get smaller, the angular velocity gets bigger if the amount of angular momentum there is going to stay the same. Next page. What's on the next page is one more example, and then a little summary, because perhaps to your relief, we have come to the end of the section of the course that deals with rotation. And we're going to take a look back over a few of the, kind of summarize a few of the things from the past 3 weeks, and maybe even fill in a few things that I didn't really point out as we went by. But before I get to that, a collision. When we were looking at linear momentum, there was lots of examples involving collisions. Well, let's have a collision that involves rotational motion. I tried to think of the stickiest projectile that I could, and what I came up with is actually a little more than a whole pound of roofing cement flying along at about 55 or 60 miles an hour. And actually at that speed, it would probably just splatter all over the place when it hits something. But we're going to assume that it ends up stuck to the edge of this wheel after the collision. So this large wheel, and actually this is very similar to what happens in lab number 9. Okay, you might want to have this example in mind. What you've got for that is there's a ball that comes down a ramp. You know, the apparatus is right over here. Yeah. It's all taken apart now. I don't feel like putting it together right now. You can just click down to the other video and come back if you want to look at it now. But you get a ball moving, it's a steel ball. It rolls down a ramp to get going. And then there's a wheel in a horizontal plane with an arm that kind of sticks out. And there's a rubber cup right where it'll catch the ball. So we don't need anything particularly sticky to accomplish the same sort of thing, but it's very much the same sort of thing. You start out with some sort of an object moving along a line, and it collides with something that'll rotate, and the question is, how fast is it going around afterward? So this would be an inelastic collision. A great deal of the kinetic energy in this ball gets converted into heat during the collision as the tar kind of mooshes around, or in the case of the lab, there's friction as the ball slides into the cup. So everyone, well, not everyone, but some people always seem to have the impulse to use conservation of energy for everything. And, you know, there are other conservation theorems besides just energy. Energy, mechanical energy is not conserved here. Some of it's changed into heat. What is conserved is angular momentum, because it's a system with no external torques on it. Okay, this two-body system, the tar and the wheel, there's no external forces creating any torques. So that's the background information. The solution goes like this. Total angular momentum before equals the total angular momentum after the collision. And before, here's the situation. You know what? That's going to be right in my way before I'm done. I'm going to put it up here. Now this blob of tar is moving along a straight line, but it does have angular momentum relative to this origin here at the center of the wheel. That's the path it's following. It's the line of action of its momentum. Okay. So mass times velocity is momentum, and there's the radius vector, which makes an angle theta with the momentum vector. So L initial, angular momentum before the collision. Well, we only really care about how much angular momentum it has. The direction, as with all of these other rotational quantities, the angular momentum vector is an arrow in the z, well, in a plane perpendicular to this one, which in this case would be the z-axis. But if we're just concerned with how much angular momentum there is, I'll slap some absolute value signs onto it. Magnitude of a cross product is the magnitude of the one vector times the magnitude of the other vector, P equals mv, times the sine of the angle in between. Well, at first glance, this might look like it's not very nice, because as this object moves along, R keeps changing from one moment to the next. as it approaches the y-axis, which I never labeled. My 9th grade math teacher would probably yell at me. As it moves along, r gets shorter and shorter, theta gets larger and larger. So both of these things are constantly changing. But the good news is, taken as a unit, r sine of theta, see, r sine of theta is that distance right there. Hypotenuse times the sine equals the opposite side. R sine of theta does not change as the thing moves along. Going back to when I first started talking about torque, remember the idea of a moment arm? Moment arm is the distance from the pivot point to the line of action. So that dotted line I drew is the momentum's line of action. This is the perpendicular distance from the axis of rotation to that line of action. And that's given right in the question. It's labeled on the picture, 1 meter. Okay, so angular momentum, the moment of the momentum. The momentum times the length of the moment arm, 1 meter in this case. Filling in numbers for m and v. M is half a kilogram. Velocity, 25 meters per second. So 12.5 I'm not going to try and say all that. Let's just go with 12.5 in SI units. So that's, before the collision, the wheel is stationary. All of the angular momentum is in the approaching chunk of tar. And after the collision, the angular momentum is shared between the disk, which is now rotating, and the tar, which is now stuck to its outer edge and moving around in a circle with it. Okay, so from over there at the other end of the blackboard, I've got 12.5 to stick in for the initial angular momentum. Over on this side of the equation, it's going to be more convenient. You can kind of see it right on the edge of the picture here. L equals I omega. Since the angular momentum is the thing that I'm looking for, so find its final angular, or I said that wrong. The angular velocity is the thing I'm looking for. It says find the final angular velocity. So using an equation that contains the thing I'm looking for sounds like a good thing to try. So let's calculate these final angular momenta from I times omega. For the tar, all of the tar is located at the same distance from the center. It's attached to the outside edge of the wheel. So MT, T for tar, mass of the tar, that's the half a kilogram again, times the radius squared of the circle that it's moving around in. Okay, it's basically behaving like a, well, if not exactly a point-like particle, but it's all at the same distance from the axis, so it's just mr squared. Disk, you've got mass distributed from the center all the way out to the edge. D for disk, mass of the disk. So moment of inertia of the disk times omega, moment of inertia of the tar times omega. And I've got numbers I can put in for everything else, and I'll solve for omega. For this, 0.5 kilograms, 1.2 squared, because now it's on the outside edge of the wheel and riding around in a circle with a radius of 1.2 meters. And that's equal to 0.72 when you multiply that out. Over here, kilograms, 1.2 meters, and that comes out 14.4 for the moment of inertia of the disk. Okay, we're closing in on it now. We're almost there. That plus that adds up to 15.12, and you divide .827. It's built into the equation, L equals I omega. It's built in that you are measuring in radians per second. One more time, don't try to use conservation of kinetic energy. It's an inelastic collision. Okay. A summary of rotational concepts. Finish off not only section 9, but actually the whole section 7 through 9. Actually, let me put that a little higher. I can aim the camera lower too, but it's so much easier to just stick another book under it. All right, the book's a little too thick, isn't it? No, not that far. Ah. All right, that's more or less where I wanted it. I'll have to lower it down a little in a few minutes, but I tried to point out as I was going along how we were recycling a lot of the same concepts from earlier in the course when I was talking about motion along a line, motion from place to place, translational motion, in other words. A little bit of background, a time derivative is the rate of change with respect to time, whereas if you differentiate with respect to x, that's the rate of change with respect to position, okay? This would give you something like meters per second, whereas, well, we'll get to that. Anyhow, the story begins with an answer to the question, where are you? I am here, okay? This radius vector, its components are the coordinates of the point where I'm located. Once you've defined an answer to that, in section 1, it was just x. Where are you on the x-axis? A few weeks later, I generalized it to motion in a plane, where your position is given by this radius vector. Next step, how fast are you moving? The rate at which your position is changing is called velocity. Remember, a time derivative is the rate of change with respect to time. So the rate that your position changes is your velocity. The rate that your velocity changes is your acceleration. Mass times velocity is the definition of momentum, okay? Where m is equal to mass. One way of thinking of mass, by no means the only way of looking at it, but one way of thinking of mass is that mass is what tells you how much momentum you have going at a given speed. Then we come to the concept of force. This is Newton's second law. I never wrote it quite that way before, but here. Momentum is mass times velocity. Well, mass is actually not always a constant. You can get involved in, for example, a rocket. As it shoots up into the sky, it's constantly losing mass that's being expelled out the back, and that can get kind of complicated. But well, as long as you don't, this is supposed to be a freshman level course. Let's not talk about rockets, okay? So as long as the mass is a constant, when you take a derivative, constants just sit there and do nothing. So that would be the mass times the derivative of the velocity. And there is the more familiar version of Newton's second law, F equals ma. But if you want to get kind of more general about things, force is equal to the rate at which momentum changes, okay? F is equal to dp dt, Newton's second law. So all that was written out here in these parentheses, that the derivative of the momentum, assuming a constant mass, the derivative of the momentum is just m times a. Well, I've got a couple other things written down under here, but let's go over here for a while, and then maybe I'll come back. So rotational motion. Once again, you start out with an answer to the question, well, I guess I said, where are you over here? But, if you started at the origin, it would be, how far did you go and which way? Your displacement. How far did you go when something is spinning is an angle. And if you include the direction with that, it's a vector pointing along the axis of rotation in a right-handed sense, the way I've drawn it here. Just as velocity is the derivative of how far did you go when you're talking about translational motion, angular velocity is the derivative of how far did you go when you're talking about rotation. And just as acceleration is the rate that the velocity changes, angular acceleration is the rate at which the angular velocity changes. Well, then we come to angular momentum. Basic definition is R cross P, but the thing that corresponds better to what we had over here is, mass describes something's inertia with respect to translational motion. The inertia times how fast you're going is the momentum. The rotational inertia times how fast it's spinning is the angular momentum. Well, then we come to torque. Torque is equal to the rate at which the angular momentum is changing, just like force is equal to the rate at which the linear momentum is changing. And I've got a bunch of things in parentheses under here also, just as P is equal to mv, and that leads you to the force equaling m times a. L is equal to I omega, which leads you to the torque equaling I times alpha. In addition, if you take this definition for angular velocity and take the derivative of that, that leads you to the torque equaling R cross F. Torque is the moment of the force. Angular momentum is the moment of the momentum. Well, then, a little further down the page, I'll just lower the camera so you can see the rest of this. There was work and energy. Force times displacement, dr or ds, whatever letter you want to use for the displacement, is the amount of work done in some small displacement. Torque times the angle gives you the work. Oh, typographical error. Should have been a little arrow over the top of the theta. Well, can't win them all. Notice that, let's see, the derivative, or well, the differential of this would be I times omega, which would be, no, wait a minute, what did I mean by that? This would be I omega d omega. It's a form of the work energy theorem. Oh, that's what I was thinking. Work equals the change in the kinetic energy, just like back over here, work equals the change in the kinetic energy. It's the work energy theorem for translational motion here, for rotational motion there. And finally, we have the definition of power, which would still be the same thing if I felt like writing it over there. Anyhow, if you see how the same concepts are recycled, this corresponds to this, that corresponds to that. Well, there are a few new relationships here and there, but an awful lot of stuff is just the same old equations repackaged. For example, from earlier in the course, P equals mv. Momentum is mass times velocity. Well, if you look at what corresponds to what in my little table here, momentum corresponds to angular momentum. Moment of inertia corresponds to mass, okay? Mass tells you how much momentum you have at a given speed. The moment of inertia tells you how much angular momentum you have at a given angular speed. So M corresponds to I, maybe I should be pointing down here. P corresponds to L, M corresponds to I, V corresponds to omega. If you got the little table, you don't really need the formula sheet because it's the same formulas over again. Now, let's finish with a word of caution. It's kind of handy to see how this thing is like that thing. Somebody gets back from a Yeah, the lights in this room are on a sensor and I'm not moving around enough apparently. Had to stand up and wave my arms around for a moment. Anyhow, somebody gets back from Greece and you ask them, what was it like? People understand new things by comparing them to things they already know about. What was it like? Well, this is like that, and this is like this, and that can be helpful in some ways. But on the other hand, the risk here is getting them mixed up with each other. The most common mistakes in this part of the course involve, I give you this, but you used it for that, or I give you this and you used it for that. Just because this is like that doesn't mean this is that. If some poet is going on about how his girlfriend is like a rose, that doesn't mean he has to spray her for bugs every couple of weeks. Analogies have their limitations. And so be wary. Do not mix these things up with each other. And that, I guess, is all I have to say about section 9. So that got all fuzzy, didn't it? Well, it's too late now. I'm done.